As we get started today, we are, as I said in my email, about a lecture behind. That's okay, no big deal. I built some flexibility into the schedule later on. If we get close to the exam and we're not quite done with the chapter that I've intended to be done on, I'll just adjust what's on the exam anyway. So don't worry about it. If you're done with the study guide on chapter 13 today, that's great, and you should be starting on the one for chapter 14. We didn't get to chapter 14 last time, and actually we're just a little bit behind to where I wanted to be even starting today. So we'll try to pick that up today. And moving on to chapter 14 next time. Yeah? Questions? Okay, good. All right. So last time at the very end of class, I introduced you to this problem of what happens when the product of a reaction is more reactive than the starting material, or at least as reactive as the starting material. When your starting material is an acid chloride, lithium aluminum hydride delivers a hydride to the pi star, breaking the pi bond, and you get this tetrahedral intermediate. And the leaving group is a decent leaving group relative to the kicker off or oxygen. And so electrons kick down and the leaving group leaves, you get an aldehyde product. Lithium aluminum hydride can't stop there because it's very reactive as a reagent, and the aldehyde is super reactive, about as reactive as an acid chloride. So another hydride gets delivered, you get this tetrahedral intermediate. Then as you look at that kicker-offer group relative to the nucleophile that got added, the potential leaving group, there aren't any good leaving groups. You're stuck until aqueous workup, whereupon you add water, and that protonates the carbonyl oxygen, what used to be the carbonyl oxygen, and you get this primary alcohol product. So the detail to memorize is that the lithium aluminum hydride cannot stop at the aldehyde, but will go all the way to the primary alcohol. Okay, and some of you might be like, well, what if I only added one equivalent of lithium aluminum hydride? There's some actual technical reasons why even that won't work. So for now, we're going to assume that you've added enough lithium aluminum hydride that you're going to go all the way to the primary alcohol. You can't stop at the aldehyde. That's also true for esters, because again, in esters, the key issue is you have a decent leaving group relative to the negatively charged oxygen. So as with the acid chloride, so with the ester, so with anything that has a decent leaving group relative to a negatively charged oxygen, that might include anhydrides or other things, lithium aluminum hydride really can't stop at the aldehyde. So organic chemists go ahead.
Does that include a methyl group?
Sorry, if it were a methyl group?
Yeah, the yellow leaving group.
Yeah, if the yellow group were a methyl group, no, that can't leave relative to a negatively charged oxygen. So if you used lithium aluminum hydride there, you would get to this point where you had added the hydride, you've got no good leaving groups, and so there you're stuck until aqueous workup. Yep. So for aldehydes and ketones, lithium aluminum hydride adds one hydride, and then you don't have any more options after that. But if you've got good leaving groups, yeah, the leaving group leaves, and then you go again. All right. So organic chemists like to have options, and especially if you can keep the starting material the same but use a different reagent and get a different outcome, that's highly versatile, very useful. So your text presents two alternatives that can indeed stop reducing agents, two alternative reducing agents that can indeed stop at the aldehyde. It doesn't really provide any explanations for these, and I'm not going to either. You're just going to have to memorize them. There are explanations, and if you want to know more, we can talk about them. You come to my office and we'll talk about them. It'll take about 3 minutes to show you how one of these works. The first is called diisobutyl aluminum hydride, or DIBAL for short. This is its structure. If you look at that, you'd be forgiven for thinking, hey, there's not even a negative charge on the aluminum, so how is that nucleophilic? You are right, and that is a clue to how it works, but come talk to me if you want to know more. In any case, DIBAL will react with esters, but not with aldehydes, so it can stop here at the aldehyde. The second reagent is unpronounceable and difficult to write. There are alternative ways to write it. This is the structure. Lithium is the counter ion. It also involves aluminum and a hydride, but the three other things attached to the aluminum are these tert butoxy groups. So there are a couple of ways you could write this down on paper. This is one way of abbreviating three tert butyl groups. If you want to pronounce this, I don't know why, but you could call it lithium tris tert butoxy aluminum hydride, which I won't ever say again. We'll just call it that weird aluminum reagent. This is a little bit less reactive than lithium aluminum hydride, presumably because of the electronegativity of the oxygens, which should pull electron density away from the hydrogen inductively. And so it's probably the electronegative oxygens that make this a little bit less reactive than lithium aluminum hydride. Because of that, it can also stop at the aldehyde. As far as I can tell in your text, it often uses dibol for the esters and then the weird lithium aluminum reagent for acid chlorides, though it tells you it doesn't tell you at all that you have to use one for one and the other for the other. So we're going to assume that you can use them interchangeably for both acid chlorides and esters. You're going to have to memorize that. You're going to have to memorize that both of these reagents reduce acid chlorides and esters to aldehydes. Speaking of memorizing reagents, do whatever works for you for memorization. I recommend perhaps, if they're helpful to you, flashcards, 3 different formats. One in which you start with the starting material and you write down the reagent and you have to fill in the product. Another in which you do starting material and product and you have to fill in the reagent. And then another in which you put product and reagent and you have to think backwards to what the starting material was. If you do that, that can help you with memorization. Yes?
When aluminum hydride reacts with chloride carbonyl, what's the final product?
When lithium aluminum hydride reacts with the acid chloride, you get the primary alcohol because you can't stop at the aldehyde.
Okay.
Yep. Yeah.
You said that these can be used for esters and for acid chlorides. Can they also be used for like thioesters?
There's no examples of that in your text, so I don't know. It would be a sensible thing to try, but I just don't know. All right. Yeah.
The lesser active version of AlH4 is it comparable with NaBH4?
Is that comparable with sodium borohydride? I don't know. It's a good question. Sorry. What else? So, all right. That sort of concludes our hydride delivery reagents. What we're going to do now is introduce carbanion delivery reagents. These are reagents that are going to deliver basically negatively charged carbons as nucleophiles to the carbonyl carbon. Now, why do we need a carbanion delivery reagent? Well, essentially the same problem we had with trying to use H- as a nucleophile. If you want to use this as a nucleophile, you have to make it, and if you think, oh, let me just deprotonate an alkane, good luck to you because the pKa is like 50. So you can't really make the carbanion directly. You need an alternative approach. And the alternative approach is to use some things that involve metals. They are called organometallic reagents. We basically are using metals to stabilize a negatively charged carbon. And so there are going to be 3 kinds of organometallic reagents that we'll talk about, but really only 2 classes. The first 2, organolithiums and Grignards, are going to be interchangeable. You'll not find any explanation in your text as to why you'd want to use one versus the other. The reasons why you'd want to use one versus the other are mostly practical and related to how much a reagent costs and how long it takes to make it and how shelf stable it is. But why give you two instead of just one? And the answer is organic chemists like having options to do two different ways to do the same thing, because maybe one will work one time, and then if your molecule's different, maybe there's some other issues. So the author of the text wants you to know about both options. The second is called so you got the first two, organolithiums and Grignards, that are basically interchangeable. The third is weird, and those are called organocuprates, and we'll spend some time talking about those. Let's start with organolithium reagents. You make these, and your text will expect you to be able to do this in some synthesis problems, starting not with the alkane, but with the alkyl halide. And then you add lithium metal. The superscripted 0 here means that the metal is in its oxidation state. The reaction that goes on is called halogen metal exchange. We're not going to draw a mechanism or really talk much more about what this reaction is. It basically involves transfer of electrons one at a time from the lithium metal to the anti-bonding orbital for the carbon-bromine bond. Ultimately, that breaks the carbon-bromine bond and makes a new bond between carbon and lithium. You've never seen, presumably, a carbon-lithium bond before. It has substantial covalent character, though it's okay to think about this reagent as the carbanion and a lithium counterion. That's not how it actually is. In fact, what I showed you here is probably even still an oversimplification for what this reagent actually looks like in solution. There's some evidence that some of the lithiums are bonded to more than one carbon, and you get interesting cage-like complexes. But in any case, it's okay to think about this as a negatively charged carbon nucleophile. And you can think about the lithium kind of in the same way we thought about the aluminum or the boron for the hydride delivery reagents. This is something that's going to carry the negatively charged carbon to where it needs to go. So let me show you an example of how you might use this. Here is an aldehyde. Here is an organolithium reagent. The lithium carries the carbon, the negatively charged carbon, to the ketone. The carbon-lithium bond breaks, and electrons in that bond attack the pi star, breaking the carbon-oxygen pi bond to get this intermediate, tetrahedral intermediate with a negatively charged oxygen. Here is the group from the organolithium reagent that was added as a nucleophile. Here's the kicker off or oxygen. Here is the hydrogen. We don't have a good leaving group, so we are stuck until aqueous workup, whereupon the negatively charged oxygen in the tetrahedral intermediate removes a proton from water, and we get as our product this secondary alcohol by reacting our nucleophile with an aldehyde. Okay? Now, it's not worth memorizing that aldehydes react with organolithium reagents to give secondary alcohols, because you can figure that out if you understand the mechanism. Yes? Yeah, the bond between lithium and carbon is high energy enough that that dumping it into the carbon-oxygen pi star is reasonable. That's why I said it's fine to think about this as being this carbanion. You wouldn't have any trouble looking at this and saying, oh, the highest energy electrons are on the negatively charged carbon. And that is how the organolithium reagent reacts. Yep. Yes?
If the organolithium reagent, for that first step, be done in an aqueous solution, or would the organolithium reagent steal a hydrogen and just make
Great question, and yeah, that's an important limitation of organolithium reagents and Grignards. They react as basically very strong bases as well. So it would be a terrible idea to use water or a protic solvent, any kind of protic molecule as a solvent, that is a molecule with a somewhat acidic proton, because the first thing to happen is that your organolithium reagent is going to steal a proton from your solvent. So yeah, one important limitation is you need to use aprotic solvents only. Now, I'm not big on writing down solvents for every reaction. Your text will do that to some extent. I tend not to, but that is an important practical issue. When you do one of these reactions in the 353 lab, you will notice that the solvent that you use is not an alcohol. It doesn't have acidic protons. Ether solvents are generally good for organometallic reagents. One example of that is diethyl ether. Another example of that is a solvent that we call THF that we may circle back to another time. Yes?
With those carbon chains on the lithium, do they have to be 2 carbons or can they be longer?
Oh, the carbon that's on the organolithium reagent, it could be any number of carbons. Yep, yes.
When you said that we should only use aprotic solvents, is that only for organolithiums or for all 3?
Organolithiums, Grignards, and cuprates, you don't want to use protic solvents, yeah. So on the other hand, yeah.
Do we need to memorize the ether solvents?
Don't need to memorize the ether solvents, but you need to not be distracted by them if you see it in the Smith text. Okay, good. So let's now see what happens when we take the organolithium reagent and react it with, say, an acid chloride or an ester. I'm just going to use an acid chloride. To emphasize that this doesn't need to be just a 2-carbon chain, let's use phenyllithium, which is a benzene ring. As before, you expect that the group, the carbon that's attached to the lithium, will take its electrons from the carbon-lithium bond and attack the pi star, breaking the carbon-oxygen pi bond. You expect to get this tetrahedral intermediate with a negatively charged oxygen. Here's your new bond with the carbon group. Here's the oxygen, and here is the chloro-leaving group. Negatively charged oxygen kicks off the chloro-leaving group, as we would expect, and you get this intermediate. I'm calling this a ketone intermediate and not a product because we have essentially the same problem here that we had before when reacting lithium aluminum hydride with an acid chloride. That is, the ketone is very reactive. And we can't stop here because another equivalent of the organolithium reagent will attack the pi star. I'm going to abbreviate what I've drawn here as phenyllithium. That's the abbreviation. Another equivalent will have the carbon of the benzene ring take its electrons and attack the pi star, generating this tetrahedral intermediate, which I'm going to abbreviate like this. At this point, I've added 2 phenyl groups to my molecule. I have a negatively charged oxygen, but no good leaving group, so I'm stuck until aqueous workup, whereupon the carbonyl oxygen attacks, what used to be the carbonyl oxygen removes a proton from water, and we end up with this tertiary alcohol product, in which 2 of my organolithium reagents show up attached to what used to be the carbonyl carbon. Okay, so that's maybe a memorized detail. You're going to need to memorize that the organolithium reagents and the Grignard reagents don't stop at the ketone. They go on to react a second time. But hopefully there's a space in your brain for that because we've already dealt with that problem with lithium aluminum hydride. Yes?
Does this also work for phenyllithium?
Does what work?
Like making a 30-prime alcohol?
I'm sorry, I didn't understand. Does this always work?
Does this work only for phenyl?
No, any organolithium reagent will do this. Yeah, it doesn't have to be. You'll notice in my example here, I changed what the organolithium reagent was. These are specific examples, but they're not limited to this. You could change the organolithium reagent. I'm sorry, was that your question?
Yeah.
Okay.
So how do you tell when like, two, like 2 or 3 prime alcohol?
How can you tell whether you should get a secondary versus a tertiary alcohol? Well, you pay attention to the starting material and whether or not the Y group is a good leaving group. For the aldehyde, you get to the tetrahedral intermediate and there's no good leaving group, so there you're stuck. For the acid chloride, you get to the tetrahedral intermediate here and there is a good leaving group, and so that gets kicked off. You go to the ketone and then we react again. Okay, others? Yeah.
So with does the benzene group make it very reactive? Is that any different than say the hydrogen leaving group or co-leaving group?
Is this benzene ring a good leaving group? No.
It's more, does the benzene ring make it more reactive than the hydrogen?
Where? I'm not certain I understand.
I'm just kind of confused because in the previous one there was talking about all of like where it stops at a certain point. I don't know, I'm just trying to
Okay. The reason we stop here, so above the benzene ring here is the nucleophile. Same thing here with the ethyl group. The leaving group we're talking about is what was attached to the carbonyl carbon, a good leaving group. As my mother sometimes says, you're cutting and I'm not bleeding. So you want to try one more time and see if I can get it?
I'm probably just not phrasing what I'm thinking very well. I'm sorry.
No, try again.
I'm just confused by the phrase very reactive. And it's not.
The ketone, well, okay. Why I said that is, as we learned earlier a couple of class periods ago, ketones and aldehydes are at the top of reactivity, including acid chlorides. When you're that's true even when the benzene ring is attached to the ketone. The point is that the aldehyde product competes with the acid chloride starting material for reactivity. Yeah. This is just as good as an electrophile as that. So this is going to go react with the organolithium reagent again. Yep, go ahead.
If you were to use citrate instead of organolithium to react with the acid chloride, would it stop at the ketone?
Right, we will talk about that in just a couple of minutes. If you used a cuprate instead, then yeah, you could stop at the ketone. That's one of the weird things that cuprates do. All right, I'm going to gloss over really quickly the Grignard reagents because there's not really a lot to say about the Grignards that's not said above about the organolithium reagents. These are interchangeable with the organolithium reagents. Grignards you get by taking the same starting alkyl halide and reacting it with magnesium metal. The way you draw a Grignard reagent is like this, or alternatively like this, but it is okay to think about as though it were the carbanion, a magnesium 2+ ion, and then Br-. But what I said here, what's true for the organolithiums is also true for the Grignards. So I'm not going to repeat that by drawing out specific examples of Grignard reagents reacting with aldehydes or ketones or acid chlorides or esters. You'll need to make sure you do that in the study guide and can follow along, but what's true for the organolithiums is also true for the Grignards. That is, if a Grignard reacted with an acid chloride or an ester, it would also not stop at the ketone, but go all the way to the tertiary alcohol. Okay? Does that make sense? Yeah.
Are we to assume that we need 2 equivalents of the organometallic reagent?
Yes, you'll assume that if you're starting with an acid chloride, you've got enough of the organometallic reagent to go all the way. The point is, you don't need to specify just one because it doesn't work to add just one. You get a mixture of products. Okay. Another thing to say is that I want you to start to get good at looking at products, structural features in products, and linking that in your mind to a reaction that could have generated that product. For example, look at that tertiary alcohol in which 2 of the 3 groups attached to the tertiary carbon are the same. If you see that, that probably is a clue that you could have made that product in one step from an acid chloride and an ester, or an ester and an organolithium reagent, because you're going to add 2 of the same one. Okay? Yes?
So, why is, like, when making the either organometallic reagent, why is this metal prime?
I'm sorry, you said prime. I didn't quite catch that. Could you say it again?
Like,
Oh, so the 0, the superscripted 0 means that this is the metal in its 0 oxidation state. That means it's just the metal, not the metal in its positive, not one of the metal ions. Okay. Now, we need to talk about cuprates, which are weird. It turns out you make cuprates from organolithium reagents. And you've learned how to make organolithium reagents above. It turns out, and we're not going to say a lot about the structure of the cuprate reagent, you add copper iodide, that's copper in its +1 oxidation state, and you end up forming 2 new carbon-copper bonds with a negative formal charge on the copper, and then lithium is a counter ion, and then you also make as a byproduct lithium iodide, which we're going to forget about. So you sort of need 2 equivalents of organolithium reagent to make a cuprate. This is your first example of an organometallic complex. We will circle back to organometallic complexes in chapter 28. We're not going to say a lot about their reactivity and how to think about them. For right now, it is okay to think of the cuprate as a carbanion and a neutral copper carbon compound. Some of you are going to get confused because you've looked at the cuprate and you've noticed that there are 2 carbon groups attached to the cuprate. So naturally you're going to be thinking, does the cuprate deliver both of them? Turns out for the chemistry we're going to see only one of those R groups is involved for reasons that we're not going to talk about because explaining them would require us to delve into organometallic complexes, and we don't want to do that yet. Some of you are probably also wondering, what if the cuprate has 2 different R groups? Which one gets added? I don't know, and for that reason, the cuprates we use will always have the same R group on them, so that's not an issue. Okay? All right, so cuprates are weird. They have unique reactivity, and we need to talk about that. Anytime a reagent does something different from other reagents, that's potentially useful and interesting. So unique reactivity number 1 is that cuprates can react with acid chlorides to give ketones. We can stop at the ketone, which is something that organolithium reagents and Grignards could not do. So here is a cuprate. For simplicity's sake, I'm using diethyl cuprate as my nucleophile. It doesn't have to be that way. It could have been any number of other R groups on either side of the cuprate. You will encounter those in the study guide and problem sets. As we saw before for organolithium reagents, the way cuprates react with acid chlorides is that one of the R groups on the copper takes its electrons, leaves, and attacks the pi star of the carbonyl compound to give you a tetrahedral intermediate. Here is the chloro, here is the ethyl group that just got delivered from our cuprate reagent. Here's the negatively charged oxygen, and there's the chloro leaving group. What happens next is exactly what you expect. Electrons kick down and the chloro leaving group leaves. And that gives me the ketone, and there I stop. And that's the unique, oh, I regret drawing that stop sign, too many lines to draw. There we stop. The ketone doesn't react further. Now that's exactly opposite what you would have expected for an organolithium reagent or a Grignard reagent, and that's one of the ways that cuprates are weird. Your text gives you no explanation about why it stops. You could try to come up with one. It probably has to do with the unique reactivity of the cuprate and its structure of the as an organometallic complex. That's simply a detail you're going to have to memorize, and you're going to have to do whatever works for you personally to memorize. Okay? It's important though because it allows you to take the same starting material that we saw earlier, the acid chloride, and not go to the tertiary alcohol, but instead stop at the ketone. What I said before about looking for structural patterns in products as ways to help you categorize and remember things and make connections to reactions applies here. This product is a ketone, and it's maybe what we might call an asymmetric ketone in the sense that what got delivered by the cuprate doesn't have to be the same as this R group. So if you want a ketone, if you're working on a synthesis problem and they say, all right, pal, make this, and the two things on either side of the ketone are different, you should look at that and say, hey, I could have made that from an acid chloride and a cuprate. Okay? Good, yes?
Is it safe to assume that it works with esters as well?
Is it safe to assume it works with esters? There aren't really any examples in your text of that. So just our standard on synthesis problems is it's got to work. And number two, unless you're in the lab, don't make up chemistry. And so probably no, I wouldn't suggest proposing a synthesis where you start with an ester and use a cuprate. It might work, I just don't know, and it's not in your text. I saw another hand here, yeah.
And this ketone will be just as reactive, so you could add like a lithium reagent and add something else.
Sure, so if at this stage you wanted to use that ketone for something else, for example, suppose you wanted to make a tertiary alcohol in which all three R groups were different. Now, sure, let's use phenolithium. And now we will get our tertiary alcohol where three things are different. Yeah, good.
And you wouldn't be able to switch that because then you'd have two phenyl groups instead of the one ethyl group and a phenyl group, because it would go all the way.
If you had started with the acid chloride and just done the phenolithium,
Yeah.
then no, it would not have worked out that way because the phenolithium reagent would have gone on to react with the ketone. Yep. So seeing some reagent-based versatility and structural outcomes is really important. Yeah, go ahead.
So if we're doing like the type of questions on the example, you have to figure out the procedure of reaction based on the product. If we were to use cuprate, do we have to make sure that it's the same just because there's a possibility that if it's not one of the
I missed, if you use a cuprate, do we have to make sure that, and then I missed that part. Can you say it a little louder?
like it has to be like
Oh.
sides at the same time.
If you're going to use a cuprate, do you have to make sure that the cuprate has the same thing on either side?
Yeah, just because there could be a possibility.
Yes. Yeah, you should. You should make sure that, I mean, I won't give you, on an exam, I'm not going to give you a cuprate option as a reagent where there's two different things, because that would be silly. I have much bigger fish to fry on exams. Yes?
In the book, it lets you write out the copper, the cuprate as just your R group parentheses 2.
Yes,
Copper, is that an acceptable?
that's fine. Yep. Yeah, you can write out the cuprate as R2CuLi. That's an acceptable abbreviation for a cuprate. Okay, I want to talk about the second weird thing that cuprates do. This is going to take a little bit of setup time, so we need to make sure we got plenty of time for it. The second weird thing that cuprates do is called conjugate addition. An alternative term for conjugate addition is 1,4 addition to alpha-beta unsaturated carbonyl compounds. What is an alpha-beta unsaturated carbonyl compound? Well, let's draw one. Here's an example. There's the carbonyl. Here's the alpha carbon. There's the beta carbon. If there's a double bond between the alpha and the beta carbons, we call that carbonyl compound alpha-beta unsaturated. And you can see that the pi bond between alpha and beta carbons is conjugated to the carbon-oxygen pi bond. You learned about that in 351. If we use resonance, we can show, or we can show by drawing resonance structures, the familiar resonance structure for a carbonyl compound, in which we demonstrated at the beginning of class this semester that the carbonyl carbon is electron poor. But you can also move the pi electrons between the alpha and the beta carbons over to make a new pi bond between carbonyl carbon and alpha carbon, leaving a positive charge on the beta carbon. That tells you something about the reactivity of the molecule that says that alpha-beta unsaturated carbonyl carbons are electrophilic or reactive at 2 locations. The first is the carbonyl carbon, the second is the beta carbon, highlighting in orange the electrophilic portions of this molecule. That means a nucleophile will have to decide, do I attack the carbonyl carbon or do I attack the beta carbon? Okay, another way of saying that, though I won't show you this today, if you want to know more, come talk to me. I can show you a molecular orbital picture of what the LUMO of this molecule looks like. But another way of saying that both the alpha and the carbonyl carbons are reactive and electron poor is that the LUMO is actually also out on the beta carbon. Okay, so a nucleophile is going to have to choose whether to attack the carbonyl carbon or the beta carbon. Now, organolithium reagents and Grignard reagents prefer to attack alpha-beta unsaturated carbonyl carbon compounds at the carbonyl carbon. So as an example, if we take this starting material and we react it with, I'm going to choose an I'm going to choose a Grignard reagent now. That Grignard reagent will attack at the carbonyl carbon, breaking the carbon-oxygen pi bond and making a tetrahedral intermediate. Here's the R nucleophile that just did the attacking. At that stage, because there's no good leaving group, there's nothing to do, nothing to be kicked off. So we wait for aqueous workup, whereupon the negatively charged oxygen picks up a proton from water, and we end up with the following product, which is an alcohol. And notice that the 2 things that got added here are the R group that was our nucleophile and the hydrogen from water. They are on adjacent carbons. So we'll call this a 1,2 addition product. And this is what organolithium reagents and Grignards do. Now, cuprates have unique reactivity. Cuprates attack at the beta carbon. Okay, so let me show you how to do this. I'll refer you to the resonance structure above to remind you of how and why the beta carbon is reactive to nucleophilic attack. Here is a cuprate. As we've seen before with cuprates, the R group is going to leave the copper with its electrons, but we're going to attack the beta carbon instead of the carbonyl carbon. If we stop there, we'd have too many bonds to carbon, so we have to break the carbon, beta carbon, alpha carbon pi bond, and we're just going to put those electrons onto the alpha carbon. So here is the intermediate that's formed. In red is the new bond between the R group and the beta carbon. Here is the alpha carbon that should have a negative charge on it. And you should notice that that negatively charged alpha carbon is adjacent to a carbonyl, and so we have the opportunity to stabilize that negative charge by resonance. In other words, the negatively charged, the lone pair on the alpha carbon is delocalized onto the carbonyl carbon. This resonance stabilized intermediate is called an enolate. That may be the first time that you've seen the enolate before. You will see the enolate again tons of times in this class. And it's important to realize that the negatively charged atom is delocalized on both the alpha carbon and the carbonyl oxygen. Okay, yes?
So the cuprate attack gives us the 1,2 and the 1,4, or exclusively the 1,4?
So we'll see that attack by the cuprate gives us a 1,4 product, but we need to talk about why it's called 1,4.
But not, it doesn't give us the 1,2?
Yeah, it does not give you attack at the carbonyl carbon. Okay? So cuprates give exclusively attack at the beta carbon. Organolithiums and Grignards give you attack at the carbonyl carbon. All right, so it turns out that because that negative charge is delocalized in two places, when we do aqueous workup, protonation can happen in two places. If we protonate on the oxygen, like this, we're going to get the following product. Just label things: carbonyl carbon, alpha carbon, beta carbon, and in red was our new bond. In this product that was protonated on the oxygen, the two things that got added, the R group from the cuprate and the proton from water, are 4 atoms apart. And so we call that a 1,4 addition product. Now, if we protonate on the alpha carbon in aqueous workup, here's what we're going to get. Just continuing to label things: alpha, beta. In red is the new bond. In purple are the two things that got added. The two products we have, one is a ketone, the other is what we call an enol, and these two are actually isomers of each other. They are called tautomers because they differ in the location of a pi bond, here in the ketone between carbon and oxygen, here in the enol between carbon and alpha carbon, and in the location of a proton, here on the alpha carbon, here on the oxygen. Now, it turns out that the enol forms fastest. It's faster to protonate on the oxygen, but the ketone is more stable for reasons that we'll talk about maybe another time. So what happens is we protonate on the oxygen first, and then over time we equilibrate from the enol to the ketone. This is why we call this reaction a 1,4 addition reaction, even though the ketone is the correct final product. If you looked at the ketone, you'd say, how on earth is that a 1,4 addition product? It's 1, 2, the R group is on the adjacent carbon as the proton. And the answer is, you got to remember that the enol happens first, okay? That being said, if you were to draw a mechanism here, I'd be totally fine for you to only show formation of the ketone and forget entirely about the enol, because the enol is not your final product. But I did want you to know where the term 1,4 addition comes from. Yes?
I guess my question is, wouldn't the intermediate for enol, like, be the majority of the resonance
So yeah, if you look at the enolate and you see the negative charge delocalized on both the carbon and the oxygen, should more of the negative charge be on the oxygen because it's more electronegative? That's a decent argument. It ends up being more nuanced than that. And we could talk, you should come talk to me sometime and I can walk you through it a little bit. Okay, so with that, there's one more important topic we need to get to. So I want you to practice cuprates doing this 1,4 addition product. 1,4 addition means the same thing as conjugate addition. Those are interchangeable terms. Again, the explanation as to why cuprates attack at the beta carbon and why organolithiums attack at the carbonyl carbon, none given in your text. That is simply a memorized detail. There is an explanation for that. It has to do with some things that we don't teach undergrads until their junior or senior year in the chemistry program. So if you want to know more, come talk to me. We can have a conversation about it. But it's sort of beyond the scope of the class. Okay, so lastly, we want to circle back to the idea that all of these reagents, we need to use non-protic or aprotic solvents, that is solvents without acidic protons, because, as I told you, if we're not careful, if we've got acidic protons present, the organolithium reagent or the Grignard or the cuprate is simply going to deprotonate the acidic proton, and then you've just made a very expensive alkane, which is bad to do. So let me give you an example where this is a problem, not because of solvent, but because of the molecule you want to react with itself. So imagine that we want to do a reaction with this ketone that's also an alcohol. And imagine we have this big plan. Let's use an organolithium reagent, because ultimately we want to make this diol in which you got a tertiary alcohol here and a primary alcohol here. The problem with that is your goal is to attack the carbonyl carbon, but you've got an acidic proton here in the same molecule. I'm going to highlight it in red to indicate that is a problem, and we're going to put the big red X through the desired product because we don't get that here. Instead, the interfering functional group of the alcohol reacts very quickly with the organolithium reagent to give me benzene, lithium counterion, and an alkoxide. And there I would be stuck until aqueous workup, in which I would simply reprotonate the negatively charged oxygen and go right back to my starting material. Waste of time. So organic chemists have developed a strategy for sidestepping problematic and offending functional groups. And that is, the strategy is called using a protecting group. So the protecting group strategy involves 3 simple criteria. First, it has to be easy to install. That means fast and 100% yield. Second, it has to lack the offensive functional group, in this case, the acidic proton. And then finally, it has to be easy to remove. So let me just illustrate for you in the last couple of minutes how you could envision doing this. Imagine starting with your same alcohol and doing a protection reaction, and that's going to convert the alcohol into something, the PG stands for protecting group, that lacks the acidic proton. And this reaction is going to be fast and 100% yield. Then we can go ahead and do the phenyllithium addition reaction to our carbonyl carbon, because the acidic proton is gone. And then in a final step, we do a deprotection reaction where we remove the protecting group. It's gone. We can't tell that it was ever there, but we have successfully made our desired product through the sidestep of protection, reaction that we wanted to do, then deprotection. That's an important strategy in organic chemistry. We use it all the time. And so we need to introduce to you your first protecting group, your first set of protecting group and deprotection strategies. That's the last thing we'll talk about in chapter 13. We'll do it at the beginning of class next time, and then we'll move on to chapter 14. Okay, see you Friday.